It demonstrates whether a candidate thinks about memory bounds. Knowing that heap elements can be dynamically pruned to keep the heap size bounded is a key system optimization mindset. In high-velocity clickstream processing, logging engines emit millions of event records per second. A common interview question is to identify the top K most frequent event IDs in the stream. While it looks like a simple sort problem, resolving this at scale under tight memory constraints is a classic data engineering filter. Let's look at the naive solution and why it fails at production scale. Candidates under pressure almost always write this code. They count the frequencies using a hash map, convert the dictionary to a list of tuples, and sort the entire list by frequency in descending order. Finally, they slice the first K elements. While this works for a few test cases, sorting the entire list of unique events is an expensive and unsafe anti-pattern. This code has a massive memory leak. If we process a stream with millions of unique event IDs, the counts dictionary grows to size M. Loading this entire array of tuples into memory and executing a full sort triggers high garbage collector overhead and will crash the container with an out-of-memory exception. We must find a way to extract the top K elements without sorting all unique items. Here is the optimal solution. Instead of sorting all unique items, we maintain a minute heap of size K. We iterate through the frequency dictionary, pushing each tuple onto the heap. Crucially, when the heap size exceeds K, we immediately pop the smallest element. Since the heap sorts by frequency, the pop operation removes the least frequent item, leaving only the most frequent K elements at the end. Let's talk about production edge cases. What if two event IDs have the same frequency? Python's Min-Heap resolves this by comparing the second element of the tuple, which is the event ID. If you need a specific tiebreaker, like lexicographical or insertion order, you can customize the tuple format. Also, if K is larger than the number of unique elements, the pop step is never triggered, and the code returns all elements safely. Remember the heap bounding rule. Whenever you need the top K elements from a large dataset, never sort the entire collection. Maintain a minute heap of size K and pop immediately when it exceeds K. This bounds your sorting overhead to on log K and protects your memory. Master this pattern to write high-performance data processing pipelines. Let's analyze the full memory sorting trap approach. Time complexity, OM log M. Space complexity, OM. Spike in memory is proportional to unique elements. Fails instantly on large keyspace. Let's analyze the bounded min-heap correct approach. Time complexity, ON log K. Space complexity, OK. Keeps memory usage strictly bounded to K elements. Linear scan is highly memory efficient. The interviewer will then ask, what if the input stream is too large to fit on a single machine? Distribute the counts using MapReduce or Spark, then merge local top K lists using a minute heap on the coordinator. The interviewer will then ask, how does tie breaking work if multiple elements have the exact same frequency? In Python, heap comparison compares the tuple elements sequentially. So, frec, event_id, falls back to comparing event_id